Okay, so welcome everyone for this last edition of PRAIRIE Colloquium. So today it's a great pleasure to welcome Christian Robert, who is professor at University Paris-Dauphine and is also professor at Warwick University. Among other things, he's a member of Institut Universitaire de France. He's also the president of the International Society for Bayesian Analysis. And I guess today we'll speak to us about approximate Bayesian computation and maybe generative models. So Christian, the floor is yours for the seminar.
Thank you, Geyer. So yeah, I want to talk today about maybe a very minor thing, which is about the approximation techniques for normalizing constant, because I find it interesting from a statistician's point of view how much it relates to a wide range of things and somewhat surprisingly to GANs among other things. And so apologies for the cryptic title and for the accumulation of acronyms, but the central theme of the talk is about this technical report, number 568 by Charlie Geyer, which kind of led the way for this type of technique. So this is ongoing work with my friends Jean-Michel Morin and Judith Rousseau on this topic. So I'll start with this 91 technical report of Charlie Geyer using reverse logistic estimation or regression to approximate constants, and then try to make the link with more modern or more recent approaches like bridge sampling, NCE, and eventually GANs. Okay. The starting point from a Bayesian perspective is the difficulty to handle the notion called the marginal likelihood, which is a simple enough object that integrates the prior here times the likelihood there against the parameter. And usually we have a collection of models indexed by k, so we have to compute a collection of evidences or marginal likelihoods ek. And this appeared quite early in the story of Bayesian statistics. Historically, I think the first paper to mention it is a paper by Dorothy Winch and Harold Jeffreys in 1990. And so this object is used as a likelihood in a regular setting to decide how much support the data brings about a particular model or a particular hypothesis. So in hypothesis testing, where, for instance, we try to decide whether the parameter of the model is within a certain set, theta naught, or outside this set, the standard modeling to accommodate the existence of two different realities is to create a mixture with a certain prior probability here, pi of theta naught, that this is the truth, or for the complement, pi of theta naught complement, multiplied by probability distributions restricted to theta naught or the complement of theta naught, that I denote pi naught and pi 1. And from this prior modeling, that again gives some weight to both hypotheses, the base factor is simply the consideration of the ratio of the posterior probabilities of both hypotheses divided by the prior. So it's an odds ratio that eliminates the weight we may have given a priori to the two model. So this is the reason for the division. And when you look at the simplification, the base factor is simply the ratio of the evidences for the first model and the second model. So again, the notation has changed, but this is again the likelihood, the prior under both models. And so maybe we could even add an F naught here and an F1 here, and it would be the same. So that's the numerical quantity that relies on the data X, so X is the data, to decide which model or which hypothesis is most favored by these data X. And so the cutting point between favor or disfavor is this base factor equal to 1. So before 1, we are more in favor of theta naught complement of the data is, and above 1, the data favors more theta naught than theta naught complement. And again, one reason for eliminating pi of theta naught and pi of theta naught complement is to just bring the weight of the data and not of the prior modeling, at least in these ways, because you can notice that the priors intervene in the integrals above on both theta naught and theta naught complement. So I will not go into the justification for using the base factor, in particular the fact that in well-defined and regular models, the base factor is a consistent procedure, in that if you accumulate enough data from one of the two models, the base factor will give a sure support for that model. Namely, it will converge to either 0 or 1 or infinity, depending on which model is the one behind the data. But the motivation for this talk is rather the numerical aspects of using the base factor, because given that it integrates over two parameter spaces or two parameter sets, a likelihood that may be complicated. It's usually not available in closed forms. The integral is not manageable, even when the dimensions of theta naught or theta 1 are small. And so there exists a whole industry of producing approximations to this base factor, starting with most standard Monte Carlo methods like importance sampling, that is using importance density functions pi naught and pi 1, simulating realizations from these two importance distributions, and then reweighting these simulations with the ratio pi naught over curly pi naught and the same thing in the denominator. And so this ratio of Monte Carlo approximations to the integral will, under a minor condition, converge to the base factor as n naught and n1 go to infinity. That's the most natural solution in this setting. And of course, it all depends on the choice of this importance function first, and second, as the dimension of the parameter space increases, this requires more and more simulations, because the ratio here and there tends to be more and more extreme, in that being either close to 0 or close to infinity. So in the end, as the dimension increases, this method requires a quickly increasing number of simulations. And so, as in opposition to this natural solution, I now introduce this notion due to Charlie Geyer of reverse logistic regression, under this title of the technical report number 568, because this is the source of the method that was written by Charlie and then revised a certain number of times and then never published. So it is one of these famous unpublished technical reports that gets cited to a fair amount, and that impacted the direction of the research in approximating base factors later. And the notion is related to multiple importance sampling, which is a notion that was formalized by Arto and his student Zhou in 2000, but is behind the proposal of Charlie Geyer, which is something that is always a bit puzzling, namely that if instead of a single important sample, one produces simultaneously capital I samples of respective sizes Ti, each of the sample does produce an approximation to the expectation under the distribution pi if it is reweighted by the standard importance weight. However, if you now merge all the samples together into a single sample, and rather than keeping the individual weights, create a single type of weight that is the target distribution pi of theta it over the sum of all these proposals, weighting them by the number of simulation for each distribution, importance distribution pi j, then this approximation, despite not producing the correct sampling distribution for each of the theta its, is correct in the sense that this is also an unbiased estimator of the expectation. And so by pretending that the entire sample or the sample of samples is from this mixture distribution, we preserve the unbiasedness of the approximation, and by adding those terms, we avoid some of the nastiest features of importance sampling, which is the explosion of the weights when val I of theta it is very small. By creating this summation of proposals of importance function, we also achieve a higher stability. So there is a sort of forgetting in this representation, which is we forget from which index theta it originated, so we forget the I, but the gain is in a better estimate in the end. Of course, this can also be seen as a form of Raoult Blackwellization. We integrate out something that is eventually not relevant for pi, which is the origin of the theta it, but this is not completely correct either, because Raoult Blackwellization, if we were to take an expectation, would require a distribution of the indices, which we don't have here, and we assume that the number of simulations for each sampling density is a fixed quantity that is somehow predetermined or given. So this is the basis of this important paper by Art, Owen, and Zhu. But for Charlie Geyer, the thing goes a bit further by not only forgetting the origin, but pretending to reallocate the simulations to the importance functions. And this relates to our purpose of finding base factors and marginal likelihoods, namely that if we take the different distributions, the importance densities, as being unnormalized, that is, the true density that integrates to 1 is the product of a constant that we know or pretend we don't know, it depends, times a function tilde pi j. So this is known and this is maybe unknown. If we can produce realization from these distributions without being aware of the value of Cj, then we can exploit this simulation to estimate the Cj's. So if you look at the previous mixture that we constructed for importance sampling reasons, it involves a quantity that is known, the tilde pi j of theta, times the exponential of log of Cj, which is maybe unknown, and then the number of simulations we ran from that particular component, which is the original weight Tj. Okay, so this is exponential of here j. So this is nothing new, but I mean the trick in Geyer's resolution is to see this quantity, that is the density up to the normalizing constant, times the exponential of eta j, and eta j is log Cj plus something that is a correction for the number of simulations. So maybe if it's 1, it vanishes. So the quantity that is unknown divided by the sum of all those terms. So that's the probability that a particular simulation theta originated from the component j of that mixture. And then the trick that leads to the estimation of the CJs is to use this probability of allocation to one component. So the probability that well, theta is from var pi j to build a likelihood whose parameters would be the CJs or the eta j. So eta, which is a transform of the CJs, leads to an objective function that behaves like a likelihood, because that's a probability that they come from one of the component, to eventually estimate eta. And so that's the approach advocated by Charlie Geyer in this technical report, namely to estimate the CJs as the maximum of the pseudo likelihood, which appears for all purposes as a logistic regression on the well, densities, unnormalized densities. Okay. And so this is a bit shocking from a purely statistical point of view, because what is random is not treated as random, and conversely, we start to treat all the simulations as equal, while we know from the start from which distribution they come from. So the reverse is stressing this point, that rather than estimating a mixture distribution on data for which the label is unknown, we have data for which the label is known, and then we recover the constants by checking the overlap of the different samples across the different densities function. But again, for all optimization aspect, we are dealing with a regular logistic regression using the densities as the covariates in the multinomial logistic regression. So that's a very unusual setup, but that leads to the estimation of the constants through a form of pseudo likelihood estimator. And of course, because we are dealing with a nonlinear objective function, the resulting estimator is biased if converging. So just to make sense through a very simple example, let me introduce this example where we have only two distributions, two unknown constants, except that we set one of the two to be known. So it is we set C1 to be 1. And then we have the same number of simulations for both distributions. And so this pseudo likelihood becomes a function of C2 alone. That writes as a log of 1 plus C2 the unnormalized normal distribution here, divided by the normalized normal distribution there for both samples of theta 1t's and theta 2t's. So the unknown constant is not that unknown because it's 1 over root 2 pi. And though running a code like this toy R code is quite obvious, we produce the simulations from both normals, and then we estimate the constant by maximizing this quantity. And as the number of simulation increases, we can see that, of course, the estimate does converge to the proper quantity. These are 10 simulations, 100 and 1,000 simulations. Actually, if we even do not pretend that the coefficient to the density is 1, we do recover it running a regular GLM logistic regression as well. We recover that the coefficient is, well, it's -1 in that case. Yeah. Okay, so that's the method of Geyer, and for some obscure reason, it never got published, but again, quite cited in the subsequent literature. So let me point out a link with a much more published and equally cited method that is bridge sampling. That comes from the same goal, like for instance, computing a base factor or computing a ratio of two integrals. So if we have two posterior distributions that are known up to a constant, which is a common situation, if those two distributions operate on the same parameter space, so if θ1 is equal to θ2, then using simulations from θ2 alone, so using only one of the two models, we have an unbiased estimator of the ratio of the missing constants if we use these simulations and take the average of the ratios of the known quantities, that is, those without an origin constant. Because just by computing an integral, you just see that the ratio of the two missing constants does appear from this ratio. And that dates back actually to a physics paper by Bennett in 76, but was rediscovered or broadcasted by both Meng and Gelman and Meng a few years later. And of course, the method does work in principle, but its variance may be terrible if pi1 and pi2 are quite dissimilar. That is, if the densities are of very little common support. Now, this principle actually is much more general because that's a very simple trick of cancellation of essentially everything. If you take a dense any function alpha, well, let's take it positive to make life simpler, such that both integrals do exist, and that's about the only condition. If we have two samples from, again, pi1 or pi2, and use a sample from pi1 in this average, the sample from pi2 in that average, for cancellation reasons, all that remains of the expectation of the top and the bottom is C1 and C2. So this is not an unbiased estimator of the ratio, but this is a ratio of unbiased estimator of the quantities. And that works for essentially any alpha. So exploiting simulations from those two targets leads directly to an evaluation of the missing constants. And this is quite popular, at least in the Bayesian community. There is an R package that is quite generic. There are different extensions to, well, create artificial pi2s to estimate just one constant, and bias correcting solution like this one. Now, in the original Gelman and Meng paper, they come up with the optimal choice of this arbitrary and free function alpha, namely that the best choice of alpha is an harmonic mean, or the inverse of the harmonic mean of pi1 and pi2, which leads to this expression for the approximation to the base factor. And, well, naturally, it brings back this notion of multiple importance sampling, because we recover exactly n1 number of simulations times pi1 plus n2 times pi2. So again, both simulations are treated as if they were coming from this mixture instead of coming from one of the two. In practice, well, this is the reason why it's optimal. It minimizes the variance. In practice, there is a major drawback, which is that the optimal solution depends on pi1 and pi2 as here, while we only know pi1 tilde and pi2 tilde. So, I mean, it's not possible to write it directly, but an iterative resolution of this form of estimator does lead to a good approximation to the optimal solution. And well, the most interesting point maybe for this discussion is that the bridge sampling estimator, even though it's written completely differently, is exactly the same as Geyer's reverse logistic regression estimator. And so what's starting here as a purely importance sampling discussion, because of this implicit equation connecting alpha and the approximation, the optimal bridge sampling estimator proves to be equal to the reverse logistic regression estimator. So we are back to Geyer. And well, this I won't spend more time on that, but this is the reason why we get to the same estimator. Now, this notion of using a mixture to approximate a constant has many justification or many motivations. And I mean, the very nice thing is that, well, as regular simulation techniques, if you know a density up to a constant, and if to keep up with a Bayesian setup, we have prior likelihood as one of the components of this additive density. And if phi is already normalized, so that's a true probability density, simulating from this weighted sum of two densities is feasible by many means. I mean, first and foremost, metropolicing, without being aware of the true value of the normalizing constant. So omega 1 is about anything. It's not a probability weight because this is not a density. And so, well, that's a paper we wrote with Nicola a while ago, but it contains this idea as a side idea, which is that if at each iteration you consider the probability that your simulation is from the first component, this writes as this ratio. And so once again, you have the mixture at the numerator, at the denominator, while the numerator is what you can have used to simulate C dat E, the first component. And because this is exactly the mixture we are simulating, this converges to its expectation, and it involves the missing normalizing constant Z associated with Z, because this is omega 1 Z divided by Z that turns this one into a proper density. And so we can determine Z by solving or inverting this equation. And surprise, surprise, that produces once again the bridge sampling optimal estimate. with a different motivation, because that time the sample of the CDTs is exactly produced by the mixture. So we are not pretending it's a mixture. We are simulating exactly, but this fact that the allocation is random between the two components doesn't seem to have any impact on the estimate. That is, if the CDTs are exactly separated into two groups without any randomness in the number of simulations, the estimator remains the same. And even more quickly, let me mention a very unique paper by Kong et al., including Charlie Meng, that got published and discussed in the Journal of the Royal Statistical Society almost 20 years ago, where the estimation of the constant is reinterpreted as a Bayesian non-parametric MLE. And well, I mean, this is a slide borrowed from Meng in a later talk. That, I mean, the thing is very unusual in the sense that, I mean, this constant C cannot be treated as a parameter, because if we know Q and mu, C is known. And so the startling idea just behind the paper is to turn mu as the unknown. That is, I mean, Q is a density, you cannot do anything about it, but suddenly mu becomes an unknown, which sounds quite counterintuitive. But from that analysis, they do produce an estimator of the constant C that eventually resembles Geyer's estimator. Okay, let me skip those slides. To come to noise contrastive estimation, or NCE, that came about 20 years later, compared with Geyer, as a generic estimation principle. This was inspired from an earlier paper of Apo Ivarinen in 2005, namely to estimate the parameter of a density with a missing constant Z of alpha. And I mean, treating Z of alpha as an extra parameter is impossible when you run maximum likelihood estimation, because, I mean, first, it's not a parameter. If you know alpha, that alpha is uniquely defined, so there is no estimation there. And if you try to maximize the likelihood without imposing the constraint, well, it appears in only one spot, and the value is either 0 or infinity, depending how you write it. So maximum likelihood doesn't work when treating Z as an extra parameter. But instead of using maximum likelihood, there exist other score of functions that lead to consistent estimation without requiring the normalizing constant, the Z of alpha. And that's well, behind the NCE principle. But actually, operationally, it looks very much like Geyer. We see the difference in a few slides, namely that you do have a sample. I mean, this is statistics, so you have a sample from your distribution. The unknown alpha is of course not available, and well, here you cannot do anything about the sample. Once you have it, you cannot have more. But on the side, you can use artificial auxiliary instrumental distribution Q to produce another sample, let's say of the same size to start with, and then once again look at the allocation probability of that sample, given that the xi's come from the first model, and the yi's come from the second model. And I mean, the probability to belong to the first model is once again Cp tilde of Z alpha over Cp tilde of Z alpha plus Q, namely the mixture for the discrimination. The difference here is that if you are in sample number 1, you are allocating one probability. If you are in sample number 2, you allocate the complement probability. So there is this memory that the first sample here is not like the second sample. That is, we know the origin of each of the observations. And if, while you increase the number of simulations for both the x's and the y's, remember they are of the same size, in the limit, this sum, or the average, does converge to the expectation J of theta. So well, theoretically, the estimation of theta is maximizing this expectation. And if you look at it as a functional in F, well, the maximum of this quantity is obtained for F star equal the log of the true distribution. And the interesting point is that this doesn't require the normalizing constant, and as a side product returns the normalizing constant. So NCE as an optimization method is a correct inferential approach in the sense that this pseudo likelihood does return the true value of the parameter. So it is a consistent method. Okay, so what is the difference between NCE and Geyer? Well, in this paper by Gutmann and Ivarinen, they call it Monte Carlo MLE. And well, this is another paper of 94 in JASA. The estimation in Geyer's approach is to oppose P tilde of xi, so the true P at theta over theta naught, and when the zi's are simulated from this at theta naught, the average of this quantity to estimate directly the z. So the zi's are distributed from that one, the xi's are from this unknown P star, and well, if you maximize this, this should approximate P star. So I mean, if you just keep that in the back of your eyes. Here is a Gutmann Ivarinen approach in that it again uses this ratio, but now the log is inside the sum. Well, essentially, I'm just cartooning the thing. And so this is a different objective or goal function to maximize in theta. And in this very deep paper by Lionel Riou-Durand and Nicolas Chopin, they managed to achieve a comparison of both approaches through a trick they call the Poisson transform, which is that instead of maximizing this quantity, they use that one. Well, I mean, this is Geyer, this is Gutmann invariant, and so if you notice this extra new, the theta hat in either this one or that one will be the same as in the original likelihoods. And so what they prove that if you push the number of simulation to infinity in the second sample, you do recover the standard maximum likelihood estimator. And the most important result in this paper is that asymptotically, noise contrastive estimation is doing better than Geyer's MLE, in the sense that the asymptotic covariance matrix is larger for NC-MLE. So there is a domination result which is quite unexpected in such settings. Nonetheless, this is a remarkable intuition of Geyer. Okay, let's keep that. The other point on which we are trying to make some progress currently, which is that if we look at the bridge or Geyer approximation to the marginal likelihood, we have also the asymptotic variance, and given that we have some degree of freedom on the number of simulations from this auxiliary distribution, let's say that we have n simulation from the original or alpha n simulation from this alternative, the approximate distribution of the approximation is normal with a variance of that type. And so for a given j, it is possible to evaluate what is the optimal variance, keeping 1 plus alpha fixed so that we don't expand in the number of simulations from the alternative. And in addition, given the simple shape of that asymptotic variance, it is possible to run a form of weighted likelihood bootstrap to come up with a proper approximation and no further simulation than the 1 plus alpha n simulation already available. Okay, to continue this, I mean, there are works going on in that direction, but very recently one appeared that connected with some idea we had, or maybe unfortunately, which is about the choice of well, G or Q, depending on the slide you're looking at. So here is G. As from the start, this choice of the alternative distribution is open. Theoretically, they are all valid. However, well, there are some constraints. First, you must be able to sample from it at low cost. The density or the log density must be available. And also, it cannot be too far from Q, because otherwise the quality of the estimator degenerates. And so you find, well, different perspectives to try to learn Q in the literature. And in particular, Meng and students and former students has been trying to find ways of improving on Q using mostly transforms. And so that's what you call warped bridge sampling, where actually you turn the simulation from Q into another simulation through a transform, and the transform is chosen so that it brings Q and, well, TQ if T is a transform, and P as close as possible. And of course, this leads to a more general perspective of trying to learn better Q hat as a form of optimal choice of P. And again, there are many solutions, but one in the recent papers is to use normalizing flows. First in this short paper, and then in this very recent paper by Xing with a student at Oxford. So I think I won't describe in detail what normalizing flows are. They are simply highly parameterizable differentiable transforms that turn a density into another, and instead of focalizing on the starting density, it is chosen from the standard distribution, say a normal, and then what is optimized is a way to transform this normal into something that looks like the actual simulations from the unknown density. And so you run an optimization program, which is a form of maximal likelihood in a highly dimensional space. And you can also see it as a neural net version of density estimation. It does have a generative aspect, so you can produce relatively easily simulations from this new model, and you actually compare simulations from this pseudo model to simulations or realizations from the actual model. And so for that reason, it has links with both ABC synthetic likelihood and GANs. Okay, let me skip that. And so if I have a few more minutes, let me just mention the disconnection with GANs, the generative adversarial networks, because I mean the spirit is somehow similar, and in the sense the techniques are similar. That is, you compare actualizations from a given model with other realizations, simulations from a generative model where you can produce X's through a certain transform, as in normalizing flows. And while those generative models are interesting in dealing with intractable likelihoods, which happens in many situations, but in particular when the actual likelihood or the distribution of the data is actually the marginalization over a large dimensional space or a complex space of z's that are the latent or auxiliary variable. When this integral cannot be produced and f of yz is available, standard Bayesian approaches must look for alternative, which is this ABC solution that I just want to mention a minute. So we are now not dealing with directly with normalizing constant, but a simulation of a distribution that is such that f of x given z is not given directly, but constitutes a generative model. And the idea to overcome that difficulty is to turn likelihood free, that is not to compute something that one cannot compute, but instead simulate from this generative model and produce values of the parameter that lead to a possible simulation of y under that model. So the original lemma is that if you simulate from pi and f and wait until this z is equal to y, the resulting theta prime is from pi of theta given y. So that's a way, without computing ever the likelihood, to simulate from the posterior distribution. That is, this value is a possible value of theta because it could have produced y as the output of this distribution. So that's, of course, a possible value of theta. But actually, it's exactly a simulation from the posterior. And it's easy to establish. And of course, while waiting for data to be exactly reproduced is hopeless. So ABC proceeds by approximating this equality at two levels. First, it uses a distance that brings z and y close enough, so there is a tolerance epsilon to be fixed. And the second thing is that instead of comparing directly z and y, the method compares eta of z and eta of y, eta being a statistic or summary of the sample and the pseudo sample. So the approximation is that the outcome of this distribution or the simulation is a distribution with density pi of theta given this approximate observation. Instead of observing y, we project y onto the eta space, the space of the summary statistics, and then instead of focusing on eta of y, we condition on the fact that the observation was obtained in this ball of radius epsilon. So that's a rough, doubly rough version of a Bayesian posterior. I mean, it's a true posterior, but given this this event, which is not exactly what happened. And so, well, if we can push epsilon to be small enough, which requires more simulations, but not zero, we do have an approximation to this exact posterior distribution. So I think I'll skip the MA example, just well, to make the link with GAN. GAN is doing roughly the same thing. You have two samples, one sample true data distribution, so this one is fixed, and one from this adversarial distribution. They must be as close as possible from one another. So this one will be parameterized towards making the generated distribution to be as close as possible to the true data. And well, one interpretation of GAN is this hypothesis testing of being from either the true distribution or from the proposal one. So after, I mean, it's a matter of implementation of this idea that, I mean, I won't comment now, but actually that's again the connection with the original Geyer idea of confusing two samples from being from the same distribution. Okay. Yeah, so I mean, I'll stop here, I think.
All right. Okay. So if there's question, people can put in the chat. And yeah, feel free to ask question now or just unmute the mic. So maybe I will start. I hope people will ask questions. So, well, you briefly mentioned about theoretical analysis of NCE, where you said people have been able to derive like asymptotics for this estimator. I mean, does it mean that you have closed form expression for the asymptotic covariance, and you can study how good they are? Or?
Yes, there are closed form expressions indeed, and I think the reason is the trick behind the study is that everything becomes a function not of the data itself, but of the likelihood or the density ratio. And so and that's one reason for the strength of the method. I mean, I don't produce many illustrations for how good it is, but there is a dimension, reduction, which brings back the object, the random quantity, to be dimension 1. So instead of having x, it's not comparing x and y; it's comparing p of x and q of x, or p of y and q of y. So the data is reduced to its unique quantity of interest, that is the density of the data, and I think that's why the method is quite resistant and robust against the curse of dimensionality, for instance.
But
because it's back to dimension 1.
I mean, in practice, do we expect it to be, I mean, because you have to pay a price for not estimating the constant, I guess. But in practice, or maybe in theory, do we expect that there is a gap with the covariance matrix of the MLE, or there should be a price to pay for this, or we could?
Yeah, for parameter estimation.
Yeah, for parameter estimation.
You obviously you're obviously getting a larger variance.
But it could be as close as one wants from the Fisher information or something like this, or?
Yeah, so it's never the Fisher information, but well, there was this curve I skipped by Chopin, that there is this hidden quantity of the number of simulations from the alternative, from this importance G. And so if you're given freedom to push the number of simulations in that direction farther, you will eventually recover the MLE, you recover the Fisher information.
But if you skip it to like having equality between the two, you don't,
Yeah,
right?
no, then you're losing.
And if you go below, like square roots, I mean, it doesn't work. Like you have at least to have the same number.
No, in principle, you may have less simulation from the other. It will increase the variance, but it's somehow linear in the number of simulations. It's not you're not changing the speed of convergence.
All right, very interesting. I should learn about this. Okay, any other questions regarding also the last part?
Christian?
Yes, I guess.
Right.
Stephanie?
Yeah, hi.
Okay.
Have you tried using Hamiltonian Monte Carlo instead of the normalizing flows? Oops.
No. For me, the normalizing flows are used for the density estimation. So
Yeah, so when you're running a Hamiltonian Monte Carlo, you're targeting a distribution as well.
well, except in like if you're in a setting where you don't know that you don't know the analytic form of the target, you can still use normalizing flows and not but not HMC. So when you can produce a very good approximation, I mean, I imagine that the sample from the target is produced by a black box, or is already given.
Okay.
In that case, I can produce this approximation as a normalizing flow, and rerun hopefully more simulations from that one.
Okay.
But I think if you can run HMC, you have a side. You must have a side product of estimating the constant. But so we have not. I have something in the back of my mind. I can remember that HMC was not doing as well. But,
Okay. Well, you tried actually, so that's
not I, but yeah, someone did. Yeah.
okay. Thank you.
Okay, thank you, Stephanie. Any other question regarding normalizing flow or anything else? Everybody's shy. So you're actually doing deep learning, or I mean, are you actually using this in high dimension, using normalizing flow implemented using networks, or not really?
Well, actually, yeah, we didn't try things very involved, but the normalizing flows were this instrumental construct to simulate from. So the CEDAs we tried themselves were not of particular high dimension, but we are working on the theoretical aspect to try to understand how much the dimension of the parameter space impacts. Because again, there is this striking projection from X to the density of X. So I'm not trying to oversell it because there must be a dimension effect, but we are back to dimension one, whatever the dimension of theta in some sense.
Okay.
Well, it's just that, yeah, when you look at ratio of densities, there is a degeneracy as as the dimension increases, because it's a product, or if you think of a product of terms, it has a tendency to concentrate faster and faster with the dimension.
So the dimensionality will be back at the end.
Yeah, well, yeah, somewhere, yes. It's illusory to pretend we cannot, we just forget about it. Yeah.
All right. So if there's no more question, we should thank Christian for his talk. Thank you. Jamal is here also. And this is the last edition for this year, so stay tuned for the next one, probably in September. And have a nice summer, everyone.